All right, here is an example that puts everything together. Assume we have two cars, both of them 5,000 kilograms. One moves 2 meters per second to the left, the other one 3 meters per second to the left, the other one to the right. So, assuming all frictions, when the cars hit each other, we want to find the common velocity that they go after the impact, assuming that they stick together when the collision is finished. So that's one thing. The other thing, we want to know what is the average force between the two cars during the collision if the entire collision takes half a second. All right, so let's see what we're dealing with. What are our knowns? So we know the mass of the cars and their speed. So M1 is 5,000 kilogram. M2 is also 5,000. Now we are dealing with a multi-state, multi-phase problem. We have the cars moving close to each other. That is one phase. We have the phase of collision. We don't know what happens during collision, likely a very complicated process. And right at the end of the collision is our state of interest, where we want to know the velocities. So it's a good idea to think about states and phases of motion. So we are looking at state, let's call it a state 1. This is right before contact. Where is the C? Contact, there wasn't a C. And we have two objects, so it's a very complicated process. Object 1, well, we don't really care about the positions. Everything, at least in theory, happens very fast. We don't care and we don't know about the positions, but we know velocities. Let's call this A, let's call this B. VA1 is 2 meters per second. And I'm going to make another bracket for object 2. VB1 is 3 meters per second. But here is something that is always helpful. Assume one positive direction for your reference frame. So in this case, the velocity of A is positive, velocity of B is negative. What else do we know? We don't know the positions. Neither of the positions are known. Let's take T1 to be 0. This is when the collision begins. So that's the only information we have. Let me put it slightly differently. So this is state 1. In state 1, write it in the middle. T1 equals 0. I start my stopwatch. Also have a state 2, which is right after collision. I know, what do we know? We know time has passed. T2 is half a second later. I don't know VA2. I don't know what is the velocity. I don't know VB2. But I do know both of these are equal. Oh, come on, don't move. Equal. And let's call them a common velocity V2 that is coincidentally what we need to find. So whenever we are dealing with this multi-state problem, the question is, what kind of principle? How does the transition between state 1 and state 2 look like? And to do that, well, everything is kinematic here. But my hunch is reinforced by the fact that I need to find the impact force. I need to look at forces. So let's do free body diagram of two cars. So before collision is boring. There is no real useful information there. After collision, we don't care. Everything we care about is during the collision. So I have two cars. Both of them have some weight and some normal force. WA, NA, WB, NB. There is also some, let's draw it the other way, some collision force between them. And this force is actually likely quite complex. So we don't know the value of it, but if I want to draw F as a function of time, likely it will look some complicated profile like this. It starts from 0 when there is no contact. Immediately at contact, the force starts to build up as the material squeezes and starts to deform. You have a maximum force. Likely will have multiple maxima. And eventually, when everything settles down, the force goes back to 0. There's no relative compression between the two objects. So this, we do not know what the profile is. However, one thing to note here is that if I look at, this is free body diagram. If I look at the entire system, so this force F becomes internal. So whatever happens to the system in terms of its overall system of particle type motion is only dependent on external forces. And the external forces are only the red ones, the normal force and the weights. And both of them are by definition in vertical direction. So there is no external force, noting that we are neglecting friction. So there is no external force in horizontal direction at all, meaning that this transition that we are interested is governed by constant momentum, linear momentum of the entire system. So this, how do I change color? Linear momentum conserved. So that's very useful. And finally, what we need to find, two things. We need to find this V2 that we identified. Also, we need to find average F bar. So now let's get to the solution. So I know going from state 1 to state 2, momentum is conserved. So that is a very good starting point because momentum gives me final velocities. It has final velocity somewhere in it. And I know a lot of information about the momentum at the beginning. So I can write M1 VA1 plus M2. No, not M1, M2. This is MA, MB. MA, oops, MA VA1 MB VB1 equals MA come on, VA2 plus MB VB2. So this is the final momentum, this is the initial momentum, and they are equal. And I know quite a lot of information. I know everything on the left hand side. I do not know VA2 and VB2, but I know these two are same variable, V2, because we are stuck together. So put everything in numbers. 5,000 times 2 plus 5,000 times minus 3 equals 5,000 V2 plus another 5,000 V2. So this is 10,000 minus 15,000, which is minus 5,000, equals 10,000 V2. So from here, V2 will be minus half a meter per second. So I could very easily, noting that there is no external force or external moment on the entire system, I could calculate what happens from before to after. This is extremely useful because, for instance, trying to solve this with Newton's equations, we needed to have the exact force profile of F to calculate exact acceleration profile, and then integrate this, which was not very practical. So that is one of the powers of linear impulse and momentum, because it allows you actually solve problems that are not feasible with other methods. So that's very good. And the other part is finding this F average. So to do that, we can look at any individual of these cars. For simplicity, I can look at car A, and I know that car A starts from some momentum, it ends at a momentum, and now I know the final velocity. So I should be able to calculate the change in linear momentum, which is the amount of external impulse applied to the car. And the only external impulse is due to this varying complex force F in the horizontal direction. So I can calculate the impulse of F. Note that that's very good because I'm not looking for the value of F. I'm looking for average force, which I can write it as F dt divided by total time that has passed. This is what the average force is, essentially. Finding some F bar, that the area of this curve is the same as area of the original F. So this part, the top part, is calculable from the linear impulse and momentum. I can look at either of the two cars, but I don't know. A becomes before B. So let's look at A. I look at car A. I have M1 V1. No, not that. MA VA1 plus the total impulse in the horizontal direction, F dt, equals MA VA2. Okay, putting the numbers from here, integral of f dt becomes ma va2 minus va1. Now I know these, which is 5,000 times minus half plus 2. So 1.5 times 5,000. How much is it? 5,000 plus 2,500. 7,500. Let me double check. V8. Oh, this one. Why am I getting a positive value? Let me just check. Should be negative. Oh, this has to be number. Okay, this is minus 2. So 2.5 times 5,000. And a negative side here. That is 10,000 plus 12. This much, I think. Let's pretend that is correct. I don't know. Newton seconds. And finally, F bar is this total impulse minus 12,500 divided by the time that has taken to get there, half a second, and that is how much? Minus 25,000 newtons. So that is the average amount of force throughout that half a second collision time. 25 kilonewtons. Okay, that actually is a good number. So it is negative, meaning that the force I'm calculating is force on A. And I expect it is in the same direction that I envisioned. It is from cart B on A, is pushing A back, basically. So all good. All right, it was a longer example, but it had a lot of stuff in it. So I'll leave this here and I'll see you later.